Hey everyone, Praveen this side. I hope you guys are doing great. So today we are going to solve the problem string rotations of each other, which is an easy level problem. So let's see the problem description. You are given two strings of equal lengths S1 and S2. The task is to check if S2 is a rotated version of string S1. Note the characters in the string are only in lowercase. So we have been given two strings of equal lengths, right? Now we need to find whether S2 is a rotated version of S1 or vice versa, right? So let's see the examples. In example 1, the string S1 is ABCD and string S2 is CDAB and the output is true. The explanation says after two right rotations, S1 will become equal to S2. That is, the string here given is ABCD, right? So if we rotate it once, what will it become? B, C, D, A. And in second rotation, it will become C, D, A, B, which is equal to the S2, right? So that's why the output is true. Now in the second example, S1 is AAB and S2 is ABA and the output is true. The explanation says after one left rotation, S1 will become equal to S2. That is, if we rotate AAB one time, it will become ABA, which is exactly equal to S2. That's why the output is true. Okay. Now finally in example 3, S1 is ABCD and S2 is ACDB and the output is false. The explanation says strings are not rotations of each other. So even if we rotate it multiple number of times, it will never become equal to ACDB. Now we have understood all of the examples, right? So let's consider example 1 and we'll try to find few observations from it. So we have two strings, S1 as ABCD and S2 as CDAB. Now we need to check whether S2 is a rotated version of S1, right? So what we can do? We can consider S1 and we need to rotate it each time. As we have seen in example 1, first we'll rotate ABCD to one rotation. Then it will become BCDA, right? Now we'll check whether is it equal to CDBA? No. So we'll rotate it one more time. So after rotation, it will become CDAB. Okay. Now, is it equals to S2? Yes, it is equals to S2. Now, we can confirm that S1 is a rotation of S2, right? So, what we were doing in rotating string in each iteration, we were simply considering the first element of the string, pushing it to the end of the string and removing it from the starting, right? And here too the same. We have taken the starting element, pushed it in the backside and erased it from the start, right? So we need to perform this operation on each iteration. But how many times do we perform this operation? Till we don't regain the original string. That is, if we take the example of ABCD, we rotate it one time, it will become BCDA. Okay. We rotate it one more time, it will become CDAB. We rotate it one more time, it will become DABC. Right. But if we rotate it one more time, it will come back to the original position. So we need to perform this operation till we don't reach the original string, right? And if you carefully observe how many times we perform the operation, 1, 2, 3, 4. And what is the 4? 4 is the length of the string, right? So we'll perform this operation till string length. Okay. So this was the naive or brute force approach, right? Now let's see the code. So this is the code in C++, although the logic remains same. So the function name is rRotations and they have given two strings S1 and S2. So firstly I have taken string 1 size and I've stored the size in count variable and I'm running the loop while count is greater than 0. That's what we have seen here, right? And on each iteration I am checking if S1 is equals to S2, return true. Else take the first element, insert it backside. That is, take this element, insert it backside. After inserting it backside, just erase it from the starting position. That is erasing it from here. Simple. So inside this loop, after count number of rotations, even if we don't find S1 equals to S2, then we can simply return false here. So this was purely based on our observations, right? Now, what will be the time complexity for this approach? Here, we are running a loop of n size, right? And inside, we are pushing it back, which is O of 1 operation, but we are erasing an element from the start, which is an O of n operation. So altogether, the time complexity will be O of n square. And what will be the space complexity? Here, we are just creating variables. We didn't use any extra data structure, right? So the space complexity will be O of 1. Simple. So this was the brute force approach, right? Now, if you try to submit this solution, it will give TLA because the time constraints are high. Now, let's see how we can optimize this solution. Now, before optimizing our solution, we need to check what is going wrong with the brute force approach. Here, we are running a loop of size n, which is simple, okay. But inside, we are performing an erase operation, which is again taking O of n extra, right? So, we need to remove this time complexity, and that's what we optimize. So, if we take again the example, we were taking this character and pushing it backside, which is O of 1 operation only. But we were erasing the character from here, right? Which was getting expensive. So what we can do? So in each iteration, we have to take this character and push forward, right? We'll do the same, that is taking this character and pushing it backwards, but will not erase it. Now, and how many times we need to do? We need to do it for n times, right? So again, I'll do the same. Here I have taken A, B, C, D, again A, B, C, D. Okay. Now, in each iteration, I'll compare this window with this window. And in next iteration, I'll compare this window again with this window. In next iteration, this window with this, and next iteration, this window with this. And finally, we regain our original string, right? So I'll not erase the starting character. So not erasing the character from the starting and simply pushing it backwards will simply save my time complexity of extra O of n. Okay. So what have we done here? If you look carefully, we have taken S1, created a copy and appended it. Okay. And after appending, in each window, we are comparing. Simple. So this was the crux of the problem. That is, just don't erase from the start, directly append, where you will save your time complexity. So after we form our string S1, we can check whether in S1 we have S2 occurrence. There are multiple ways to check it. In one approach, you can use the built-in find approach. In C++, it is fine, but depending upon the languages, this may vary, right? But you know, there will be a find function. Okay. So let's see the code. How can we do this in C++? So here's the code where I am appending S1 again to S1 and assigning back to S1. With this copy will be generated. Okay. Now in this copy, I am applying find function, that is S1.find S2, whether this S2 is there in S1 or not, which is a built-in function. I am calling it. If it is present, it will return true. But if it is not present, it will return -1. And if it return -1, it will return false. Okay. Basically, we can do this in if and else condition, but since it will return a truthy or falsy value, right? So I've directly returned the comparison statement. So this is one approach. Now, what is the second approach that we can do? Before going to approach 2, what we are actually doing with S1 and S2? We are trying to match pattern S2 inside S1. So it is a pattern matching thing, right? That we are doing. So which algorithm can efficiently do pattern matching? It's KMP algorithm, right? So we'll use KMP algorithm to check whether S2 pattern is getting matched in S1 or not. Okay. So recently I have explained KMP algorithm, which is a search pattern algorithm, in detail. So if you guys know KMP algorithm, well and good. But if you don't, you can refer this video and you can build the intuition of KMP algorithm, because I tried to explain it as intuitively as possible. Okay. So the prerequisite is, if you want to solve this problem in second approach, that is KMP algorithm, you must be knowing the KMP algorithm. Okay. Now, keeping in mind that you know KMP algorithm, let's see the code. So this is the code in C++ with KMP algorithm. In KMP algorithm, we do two steps. First is generating LPS array, and second, matching the pattern. We can match the pattern of occurrences multiple times, but here we just need to check it once. So I am checking it for only once. Okay. So generating this LPS array, I have explained detailedly in the video. And again, matching the pattern, I have explained in the video. Okay. So if you watch the KMP video, it is a slide modification. In that video, I'm explaining how to store the indices of multiple occurrences. Okay. But here we just need to match the pattern, right? So at any iteration, if we match the pattern, I'm returning true. But if in the whole execution of loop, if we are not matching the pattern, then I'm returning the false. But in that video, instead of returning true, I am storing the indices. That is the only difference. Okay. So with this two-step process, you can simply use KMP algorithm and solve the problem. And for this approach that we have seen, the time complexity is O of n, since find function takes O of n time complexity. Okay. And the space complexity is O of n, because we are again appending S1 with S1 and reassigning back, right? So it is O of n. And coming to time and space complexity of KMP, the time complexity is O of n plus m, where n is string 1 dot size and m is string 2 dot size. And the space complexity is O of m, where m is size of the pattern or S2, right? Because we are creating an LTS array of the same size. So it's been a journey, right? That how we have started the problem brute forcefully, what is the pain point that we have found in the brute force approach, how we have optimized it. It's all been a journey. And I want you guys to never underestimate the brute force approach, because if we have not seen this extra time complexity, we would have never optimized it. Okay. So at least try it with brute force approach. Okay. Because then only you will feel the need why to optimize the solution. Okay. So this was the video, guys. I hope you guys like this video. If you guys have any query regarding the explanation at any point, you can comment it down. I'll try to respond to it as quickly as possible. And if you have any feedback for my teaching, please comment it down too, so that I can improve on that. So see you guys in tomorrow's video. Till then, stay safe, stay happy, and peace.